Dear students, so welcome for this particular video lecture on signal space analysis. So basically, when you are studying digital communication, it's very important to understand the concepts of signal space. So we will go through these concepts in this lecture. Um, so basically, a signal space is an Euclidean space in which we have a geometric representation of the signals, and it is usually done to have a better understanding of the additive white Gaussian noise channel and passband modulation system. So we will go through these concepts one by one. What is additive white Gaussian noise? What is passband modulation? And how a signal space concept is useful to analyze all these complex concepts in digital communication. So first, let us build upon slowly on the concept of signal space. So it says that the signal space is a Euclidean space. So what exactly is an Euclidean space? So it is nothing but it can be a two-dimensional space or a three-dimensional space, and any point within this space can be represented by some coordinates. So probably you have come across this concept in your early years of college or in your high school when you did coordinate geometry. So basically you have let's say a kind of a coordinate space defined like this. So x-axis, and then you have y-axis, and then you had a point here which had a coordinate x1, let's say, and y1, and which means that the intercept it makes with the x-axis is x1, and the intercept it makes with the y-axis is y1. So this is an example of a two-dimensional Euclidean space. So you also probably come across the concept of a three-dimensional Euclidean space defined by three coordinate systems x, y, and z. So these are example of Euclidean spaces, and we will see that how a time domain signal, which is basically a function of time, usually the amplitude of the signal or some other parameters like phase or frequency varies with time. So that can be represented as 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 a dot, as you just see here, in a Euclidean space. And how to do that, we will see gradually in this lecture. So before proceeding further, let's revise the generic communication system model that we have for a typical digital communication system. So usually we have a symbol source. So as you saw when we were doing discrete memoryless channels, we had a source alphabet that consists of M symbols, M1, M2, up to M, capital M. So these are all the symbols. MI represented generally, where I stands for 1 to capital M. They are generated from this particular symbol source, and then a transmitter maps each of these symbols to a particular waveform or a signal SIT. So for each MI, there is a mapping SIT. So whatever be the symbol MI, that is mapped to a distinct time domain signal SIT, and that signal is transmitted through the channel, and then at the receiver you decode that to get back an estimate of what has been sent. So this is how the digital communication systems work. And if the symbols are equally likely, then they all have a priori probabilities defined by pi, which is equal to 1 over m, that is the probability of its occurrence is same if the symbols are equally likely for all the symbols. And then, as I said, the transmitter associates a distinct signal SIT with each symbol MI. So this is the physical waveform or the time domain signal that is transmitted through the channel and then received and then decoded back to get back the original symbol. And each signal SIT lasts for TB seconds. So TB is basically the duration of the bit. So when you are sending, let's say, binary symbols, that is comprising of zeros and ones, like the bits zeros and ones. So the duration of the bit, which corresponds to TB seconds, the signal SIT lasts for that particular duration. So and then each signal SIT is real valued with energy that is defined by this particular expression. So you do SIT square and then integrate it over all values of SIT, and since SIT exists between 0 to TB, you are integrating between 0 to TB. But generally speaking, for a general signal, this is like minus infinity to infinity, SIT square dt. So in this case, since your SIT is defined between 0 to TB seconds, so the integral goes from 0 to TB. And then the channel is assumed to be AWGN. So this means additive white Gaussian noise channel. So the channel adds some noise that is defined by this term WT. So WT is a random process. So again, we did review of probability theory and random processes in the first few lectures. So you saw that we defined what is a random process there. So the noise in a communication channel is a random process that follows a Gaussian distribution. And it's white because it consists of all possible frequencies. So if you have different colors and if you combine all of them, then that gives you white light. So from that concept, we call the noise as white noise because it consists of all possible frequencies. And that noise is getting added when the signal passes through the channel. So that's why it's additive white Gaussian noise channel. So the received signal is basically the transmitted signal plus the noise, and then we also assume that the channel does not have any amplitude or phase distortion. So the amplitude of the signal remains the same, there is no attenuation, and the phase of the signal is also not changed. The only change happens is because of the addition of the noise. And the process WT, so the random process WT is assumed to be statistically independent of SIT. So SIT is your signal and the noise is WT, and both of them are statistically independent of each other. So then the receiver observes the received signal RT and tries to make an estimate of SIT, like tries to make a best estimate of what has been sent. And because of the noise, there will be occasional errors while you are trying to do the best estimate. So SIT has already been added to WT, so there has been some noise, and if that noise is very high, uh, or it has a very high negative value, then you might end up making a mistake in estimating SIT. So that mistake is counted as errors. And the receiver should minimize the average probability of this error. So this is very important. This is basically true for any communication system. When you design a communication system, the ultimate goal should be to have this probability of error as low as possible, close to zero if possible. And this is given by the sum of the errors due to all the transmitted symbols. So you have I symbols that you are transmitting, and for each of the transmitted symbol mi there can be an error. So you have that probability of error when you are transmitting mi, and you sum that over all values of I. And this expression, if you apply Bayes rule as you learned in probability theory, then this can be written as a product of two probabilities. So the first one is the a priori probability of the transmitted symbols, so probability of mi, and the next term is the conditional probability that given mi is transmitted, what is the chance that you are making a mistake in estimating mi. So you are observing rt and you are trying to make an estimate m hat, and if that estimate m hat is not exactly equal to your original transmitted symbol, then you are making a mistake, and that's the error. So what is the probability that you are going to make that mistake given your mi was transmitted? So that probability multiplied with the a priori probability of the symbols gives you the error due to mi, and you sum it over all values of I, and you get the final probability of error, and your ultimate goal should be to minimize this average probability of error. So having said all this, so let's look a little more carefully into the block diagram of communication systems. So this time let's assume that we are having binary communication. So what happens here, your source, um, you have a message signal, your information carrying signal mt, and your source is doing some form of source coding to generate some binary symbols denoted by bk. So bk can take values between 0 and 1, let's say. So so the modulator or the transmitter is basically mapping S1t to a 0 and S2t to 1. Okay, so whenever your source is emitting a 0, your modulator is sending S1t through the channel, and whenever your source is 1, the modulator is sending S2t through the channel, and then the channel adds some noise and you get the received signal. And in the demodulator, you are basically trying to estimate what was the symbol or what was the bit in this case, because it's a binary modulation, binary communication, so you are just sending one bit at a time. So your demodulator is trying to estimate that bit bk hat from this received signal, and then trying to reconstruct the original message bearing signal mt. So what does this imply? Um, Before that, the bits in two different time slots are statistically independent. So this is again important. So if you are emitting a zero in one time slot, uh, then in the next time slot, whether it will be zero or one, that doesn't depend on what you get in the current time slot. So this is meant by the bits in two different time slots are statistically independent, and they have some a priori probabilities. So probability of being has zero is p1, let's say, and probability of being one is p2. And then the signals S1T and S2T that are sent through the channel for a 0 and 1 respectively have a duration of TB seconds and finite energies. So we have discussed this aspect in the previous slide also, that the signals that are sent through the channel is basically it's within the duration of the bits that you are sending. So and the signals will have finite energy. So E1 is again defined as S1 square integrated over 0 to TB, and E2 is S2 square integrated over 0 to TB. So having said that, this slide gives an example like what is actually meant by, let's say, you are mapping a bit or a symbol to a particular signal. So let's say the previous rule that we discussed is like whenever we have a zero that is emitted from the binary source, we are sending S1T through the channel. So zero is mapped to S1T, and whenever we have a one, we are sending S2T. So one is mapped to S2T. So let's take an example. Let's say um, this is my message bearings uh, signal. Okay, so this is a binary signal comprised of zeros and ones. So let's say these are the numbers that are emitted from the source. So at the first uh, slot between 0 to TB, I have a 1. So this means my BK is 1, and whenever I have a 1, I will have S2T. So let's say in case of a binary amplitude shift keying, or basically this is the digital equivalent of amplitude modulation. You have come across amplitude modulation in your communication theory class. So in digital communication we call it amplitude shift keying. So in case of amplitude shift keying, whenever we have a high amplitude we have a signal, and whenever we have zero we don't have a signal. So this essentially means that whenever we have a 1, we are mapping S to T according to this rule, and S to T in this particular example of BASK is a sinusoidal wave V sine 2 pi FCT. So this is a sinusoid within 0 to TB when we have a 1. Again, when we have a 0, we have nothing. So that means we are sending essentially a signal 0. So S1T is 0 in this case. Then again, we are sending between 2 TB to 4 TB. We have two like consecutive ones. So in this case, we are sending S to T for this entire duration. And then again, between 4 TB to 6 TB, we are sending 0 and so on. In case of BPSK, which is binary phase shift keying, we are sending basically two signals. One is 180-degree phase shifted version of the other. So basically the phase of the signal changes with the change in the bit. So if we have a 1, then I'm mapping it to S2T, which is V sine 2 pi FCT. And if I have a 0, I'm mapping it to S1T, which is the same signal but with a phase shift of 180 degrees. So that's why This is binary phase shift keying. Again, in case of binary frequency shift keying, we are sending v sine 2 pi fct when we have a 0. So your s1t is v sine 2 pi fct. So we are sending this particular signal v sine 2 pi fct whenever we have zeros, and whenever we have ones we are sending s2t, which is higher in frequency. So this is v sine 2 pi twice the frequency, 2fc times t. So we are sending a high frequency signal when we have a 1. So basically the concept is that whenever we have a 0 we are sending one signal, and whenever we have a 1 we are sending another signal. So this is the scenario for a binary communication systems. You will see later in this module, like when we have MRE modulation systems where we have more than one digits sent together as a symbol, we will have different scenarios. So for example, you can send 2 bits at a time, and 2 bits together can have 4 patterns: 0 0, 0 1, 1 0, and 1 1, and then you can send 4 different signals corresponding to 4 different patterns. So this is a more general concept, but let's not go there. We will go through those later. Let's just focus on the binary communication systems, and right now you just try to appreciate the fact that in case of binary communication system, when we have a bit 0 emitting from the source, we send one signal s1t, and when we have a bit 1 emitted from the source we send another signal s2t. And s1t and s2t can be designed in many ways, and based on that we can have either amplitude shift keying, we can have phase shift keying, or we can have frequency shift keying. So moving on, and then the noise, we cannot ignore the noise. So the noise Wt, which is a random process, is stationary Gaussian and zero mean white noise with two-sided power spectral density of n0 by 2. So this means that if you take the expectation of the noise, you will get 0. So the noise is zero mean. And if you take the autocorrelation of the noise, the correlation of the noise, so basically this is expectation of Wt with another time shifted version of the same Wt, then you get n0 by 2 times delta tau. So so that's the property of the noise. So basically this is the time domain correlation of the noise. So in this case, if you look into the time domain correlation, if you plot it with t, so it's basically a sharp impulse at 0, and the amplitude of this impulse is n0 by 2. So that is what is meant by n0 by 2 delta tau. And if you take the frequency response of this noise, if you recall from your signals and systems class, any delta function in time domain will give you a flat spectrum at frequency domain. So basically this will be the frequency domain representation of the noise. So you see a flat spectrum with all possible frequencies that are present. So that's why this is called white noise. So if you imagine the received signal over time interval k minus 1 tb to k tb, then you can define the received signal in this way, where you have the input signal si, I can be 1 or 2 in case of binary communication systems. So that is defined between t So that is defined between k minus 1 TB to k TB, and and your noise is getting added to that signal, and your objective is to design a receiver or demodulator such that the probability of making an error is minimized. So now comes the concept of signal space. So you can see that your original signal is a function of time, and your received signal is a function of time. Your noise is also a function of time. So usually it's a bit complicated to analyze these random processes which are functions of time, and then calculate the probability of error, and then try to minimize the probability of error. So mathematically speaking, you need to have an expression for the probability of error, let's say, to try to minimize that. Okay, so this expression of probability of error is difficult to obtain if you keep your analysis in the time domain or in the waveform domain. So basically, instead of having an observation in the time domain, if you have any mechanism or means to observe the signal and the noise as just a set of numbers, which are random variables, then it's easier to calculate the probability of errors. So that is why we need the geometric representation of the signals, or we need to have a signal space representation, so where signals will be assumed to be dots in a coordinate system. So we have to find out or define that coordinate system where, by some miracle, let's say a signal, let's say this is XYZ coordinate system, and in a signal, instead of looking like a time domain signal like this, will just look like a dot uh, in the signal space, and then this is basically a number that is defined by its XYZ coordinates. Okay, so this is what we want to do. We are here and we want to go here. So that's what we will learn, how to represent a time domain signal in a coordinate space as a dot, and then we will see if we can do this from here to here. We will see like how easier it becomes to analyze the problem of calculating the probability of error and minimizing it. So in general, we can represent signals in many ways. So we can have, let's say, magnitude and phase representation. We can have the quadrature representation. We can also have the complex envelope representation. So so magnitude and phase representation is given by this. So let's say we have a signal ST, and we have a certain magnitude which can be a function of time or which can be a constant. You saw in the examples that I showed for binary amplitude shift keying and binary phase shift keying, we were using V sine 2 pi FCT. So in that case, the magnitude was constant, but generally speaking, the magnitude can also be a function of time. Okay, and then we have the cosine or sine functions. We have a frequency and we have a phase. So so this is the magnitude and phase representation of the signal. We can represent the same signal in terms of the quadrature representation or IQ representation. So we can say ST equals to xt times cosine 2 pi FCT minus YT times sine 2 pi FCT. So these two representations are equivalent. If you see, if you see the magnitude and phase representation in the previous slide, if you just expand this cosine function using the usual trigonometric identity, then this signal will be a t times cosine of 2 pi fct times cosine of theta t minus at times sine of 2 pi fct times sine of theta t. Okay, so so if you define this and this a cos theta t as your xt, then you can write directly from here xt cosine 2 pi fct minus, again if you define at sine of theta t as yt, then you can write yt sine of 2 pi fct, where your xt is a t cosine of theta t and your yt is at sine of theta t. So you see magnitude and phase representation is equivalent to the IQ representation. So IQ representation is this thing, xt cos 2 pi fct minus yt sine 2 pi fct. So this is what you have. So it's the same way of representing the signal. So so similarly we will see that the general notion of the signal remains the same even if we represent it as a dot in the signal space. Okay, just like the magnitude and phase representation and the IQ representation are same and keeps the general fundamental properties of the signal intact, we will see the signal space representation also keeps the fundamental properties of the signal intact, but just it's a different way of seeing the signal and representing it so that it's easier to mathematically analyze the signal. Okay, so that we can obtain the probability of error and minimize it. Okay, so I will stop here and we will continue with the signal space concepts in the next video lecture. Thank you.